right, I can. So interesting news of the week, speculation, whatever it is, was that NVIDIA apparently sustained a major hack attack. And if you read various websites, they apparently had, they were broken in. Apparently, their hardware design files were stolen. And NVIDIA attempted to retaliate and managed to lock up the attacker's computer, but it was a virtual machine, and they managed to get away with that, with whatever they stole. Some people are talking about some gigabytes, some people are talking about terabytes of data. People didn't know what it was about. Some people, initial, oh, this must have been something related to the war in Ukraine. No, it was the hackers trying to bypass the low hash rate limitation so they can unlock the GPUs to do the crypto mining. Now they're posting that you can apparently download you can pay them, you can buy from them a way to get around that limitation, but I wouldn't trust that at the moment. Anyway, this is life, and reminds us all to be reasonably vigilant about how we protect our stuff. You can just imagine, design files being or design kits or anything like that being locked up, stolen from BWRC. We would be all done over here. Okay, it just takes 1 weak link, and they're in. I don't think they'll find anything useful for crypto mining, here, but who knows? Okay. So we talked about some, we wrapped up the modeling. We talked about the linear ID VGS model and the alpha power law model. Linear ID VGS model is something that I'm going to be referring to fairly frequently, and so will be the others. It is good for evaluating power performance trade-offs around a nominal VDD. It is not accurate at low supply voltages near, closer to threshold. Alpha power law is valid in a wider range, so sometimes we'll see alpha power law there. And we talked about transistor leakage. We saw that it is exponential in multiple terms, VTH and VDS. Also, what you'll find out, since there is a dependence from VTH to channel length, it also tends to be, if you're over the cliff, it can be exponentially proportional to channel lengths. And then we spent some time about talking about these nonlinear resistances and capacitances that we find in transistor models. And we talked about linearizing them. We have also figured out that linearizing really depends on the range in which we are linearizing. So high to low equivalent capacitance during high to low transition is different from the equivalent capacitance during low to high transition, and yet different than the power capacitance used in power or energy calculations. And I hope everybody knows that. It's simply because we're integrating something nonlinear across different range. I want to go quickly through standard cells here, so bear with me here. This is how an ancient standard cell used to look like. Modern standard cells have some resemblance of ancient standard cells as well, in the sense that there is a certain degree of regularity that is applied to them. However, new standard cells that correspond to FinFETs are much more regular than the old-fashioned standard cells. The old-fashioned standard cells look kind of like this. I mean, this is a good representation of a standard cell that was somewhere around, quarter micron technologies. It featured vertical polygates, possibly having some jogs at least to accommodate the contact, and sometimes there was some amount of carbon there. Diffusion was preformed. You could do whatever you want, whatever kind of a shape you wanted to have in diffusion. And here is an example of different diffusion jogs that were here to accommodate the vias down to ground and to the output node. Important thing that it had, that it featured back then, was the fact that the height of the cell, and this does not want to ink for some reason. There'll be no inking today. I tried. No, something happened here. No. Somebody knows why PowerPoint has this idea of freezing when on Zoom, and I did. And I disabled hardware acceleration. I did everything. Optimized for video in Zoom, you mean? Yeah, I did that. And I went through the support database and all of that. Anyway, I will not be doing inking. I'll just do things with my fingers, and then we'll go. I was supposed to draw something, but we'll see. And I'll make one more attempt next Thursday, and then we're coming up. So here's what's happening. What was the important feature here is the height of the cell was equal to the multiple of lowest metal routes. And typically, what you would find there was that multiple was something like 12 metal one tracks. If metal one was routed horizontally, although you see here a slight violation in that principle. Metal one is going both vertically and horizontally. That was allowed at standard cells. So, why we discussed this, right? I mean, we do want to designate metal routing to a particular metal layer, to a particular direction, so that we don't, take ourselves in the corner. It's much easier to route if metal is designated to go horizontal. So the multiples were here, you could get a 9-track cell, 10-track standard cell, or 12-track standard cell, or in some cases smaller than that. We mentioned this before. Shorter standard cells usually were, shorter standard cells, less metal tracks would result in higher density. Fuller cells would often result in higher performance. This is how you would connect standard cells. It was totally preformed. You can run level one. Some, as the cells got tighter, it became more restrictive. So the metal layers became more dedicated. They're packed next to each other, sometimes very compactly, sometimes not. And then if you wanted to have different kinds of standard cells, you would have to what you would try to do is, you would have pillar cells. So the ground and VDD lines were continuous. And then you would put them in adjacent rows such that VDDs would have been shared between them. Now, fast forward to FinFET cells, and it was not possible for me to show how they look like until ESAP7 library showed up and opened up this educational design kit. So there we see certain trade-offs that are fairly new and maybe confusing to a lot of students when first time encountered. So the first thing here that we encounter in ASAP7 and many other standard cell libraries that we're looking at the moment are that the cell height is not an integer multiple of the lowest metal. It is 7.5 track cell, which in this case means 7.5 metal 2 tracks. The reason for that is, well, because things go horizontally, poly goes vertically, metal 1 goes vertically, metal 2 strictly goes horizontally. So it doesn't make sense to define the height of that cell in metal 1 tracks and the number of metal 1 tracks. It makes sense to define the height in the number of metal 2 tracks because those are the ones that are going to be used for a horizontal row. 2, where does this 7.5 come from? That kind of sounds weird, right? I mean, I would like to maximize the number of tracks that they can run over, but 7.5 is kind of wasteful. Right? So I would like to have an efficient number of minimum with tracks that they can run over. So, well, it comes from the fact that there is this thing what they call the gear ratio. There is a difference between the metal 2 minimum pitch and the 10 pitch. So in this case, it is assumed that they survey the literature that the 10 pitch is 27 nanometers. Metal pitch is 36 nanometers. The cell height is 270 nanometers, which turns out to be 10. You can put 10 pins in there, or 7.5 metal tracks. That affects the architecture of a cell that essentially allows for a wider power rail and ground rail. Later, we'll see an implication of that, or we have mentioned that. That's quite a bit of takes quite a bit of a real estate, and it does make sense to go in the route that you're hearing now that you're going to get buried underneath a standard cell. Again, this is the world optimized for standard cells. Those of you that are analog designers will need to figure out how to live with that. And I'm sure analog design will survive transition to 3 nanometer. Okay, so this makes sense. Now we have choices that you can have 12 pin pitches, 10 pin pitches, or 8 pin pitches corresponding to 9 metal 2 tracks, half metal 2 tracks, or 6 metal 2 tracks. You actually could find commercial versions of both 7.5 and 6 metal track standard cells that correspond to this 7 nanometer, 5 nanometer node, but 7.5 track library prevailed because it allows a richer variety of standard cells. Essentially here, all what you can do is fit 2 pins in the space designated for the NMOS device and 2 pins for PMOS device, really limiting the range of widths that we can find. The cells will have to grow into horizontal direction to accommodate more fingers. Looking at the architecture relatively briefly, this is how it is, how a 7.5 track standard cell is built. So you first look at the the pins that have been pre-cut, so there would be, it is done by using double patterning of lit edge, so they would be cut at certain places to separate them. Then there will be an active region that would correspond here to something that's an N3, and something that corresponds to an inverter. There are active regions defined for both NMOS and PMOS. Then to space the cells, to define the where the pins should be discontinued. So pin block mask will be there. And one thing to notice here is there are fairly widely spaced. You will find that in TSMC libraries that correspond to this node. Essentially, the spacing needed between the two cells was equal to 2 polylines. Later, new libraries that you will see now that correspond to N5 in TSMC and all others are tighter because they managed to isolate the cells by only using a single dummy polyline. As I mentioned before, there is a leakage implication of that. And our students actually in BWRC right now are trying to figure out how to handle this in analog generators, such that they don't, that there is a balance between the, what is happening with the stress and the strain mobility of a PMOS device versus the leakage between the two cells. Right, there is essentially a polygate here that is grounded, but it tends to leak cell to cell. Anyway, this is probably flying way above, what are we trying to pick up from here, but there are some things that you may find interesting later on when you look at that. So this is showing diffusion rate between the two cells, so the pins will not be quite there. And then we see poly defined. Poly runs vertically and allows 7.5 track architecture, 3 NMOS pins and 3 PMOS pins to be captured by 1 poly. Then poly is also lit edge defined, meaning that the poly is removed down and it's basically cut on the bottom, and you have these nice poly ends at the bottom of the cell where the power rails are going to go. Contacts are done, most of them. There's something that is called the local interconnect layer, and there is a local interconnect, that goes below metal 1. This is like 2 types of metal 0. One is the local interconnect to the gate, so this will drop to the contact to the gate. And then there is local interconnect to the source and drain that would contact to the source and the drain. To avoid this issue of introducing blockages in metal 1, so local interconnect is like a metal 0 that would connect to them, and essentially there will be vias dropped to connect these cells to the power rails. They're placed regularly because you can't just have a single via anymore in these processes. And then there is metal 1 that will just connect to the local interconnect and essentially form inverter. The same way how I did it last time, except that I did not have local interconnect. So, there are a few features here that we see. We have at least 2 metal 2 tracks available for input, so I can at least fit easily, 2 inputs per N stack, and 2 inputs per P stack. So it allows for a relatively rich set of standard cells. And outputs, when connected like that, allow for all 5 metal tracks, metal 2 tracks to be routed out horizontally and used out there. Double diffusion break essentially says that in order to isolate 2 standard cells, we need to space them by 2 polylines. Single diffusion break is something that you will hear now as a feature in modern processes. Here is a picture of how does a latch look like. Not much news there. You can stare at it and enjoy the artistry of how this stuff is being put together. That's all what I wanted to say about standard cells. Beyond for around 5 to 7 nanometer or 7 nanometer to 5 nanometer. Things are changing going down to N3 and beyond. Few things that are happening here is we have these space now that generally allows us to have 2 or 3 pins here, say 3 pins in 7 nanometers and 5 nanometers to put a P device and 3 pins to put the N device down. Because the scaling is not working quite according to Moore's law, things need to be more compact, and what they're trying to do is to exploit the vertical dimension, the increase of the current by drawing transistors vertically above the plane of the standard cell. So there is this interest to depopulate and shrink the number of tracks. So going from 7.5 to 6 or 5 by increasing the pin height, as we have seen in these SCM pictures, preserves the drive strength, but makes N2 routing to the gates tricky. I can't say much more than that, but it is something that is it is interesting to see an art of getting around that. Now we have talked about nanosheets and ability to further grow the height of what used to be the pin of a transistor in the third stage. We are likely going to see things going that way, and I think the major development there needs to be in this local interconnect and ability to contact them. But that's where the industry seems to be heading now. Beyond that, we have these N's and P's. Now, after that, they're talking about a stacked or port sheet type of a device architecture, and after a stacked NP CMOS, which means that you can have one nanosheet of an N type, then a couple of them of an N type, then a few of them of a P type, and you can put them just all on top of each other. That is going to a 3 metal track or a 4 metal track architecture, making it pretty tricky. You have no more room for power rails anymore, so the power rails are to go underneath. And then all what you have to do is to figure out how to make all these 3 input standard cells up. Make sense? Any questions about this? I can ask you any question about the modern standard cell architecture. By the way, if you're interested in publishing a paper at a prestigious conference, I'm pretty sure if you investigate something, impact of these cell architectures on relatively simple designs like a miniature RISC-V, I think they'll take it. If you have time, I mean, you would have to play with, some, you'll need to find a device friend. Maybe we have one in the class over here who has a simulator of these devices. Come up with some performance metrics, read it from the papers, and then by massaging a relatively small set of standard cells, you can come up with interesting observations there. And I think you will find out relatively quickly that some of these that are presented by our device colleagues don't make sense. Some of the architectures here don't make sense. They would require another technological breakthrough in how to connect the things. But in the meantime, you can generate an IBM paper on this. Yes.
Question about when we're laying this out. Why is it that you draw out the bit and then you apply a cut onto it as opposed to just drawing out the screen? Is it because you can't do it?
Yeah, you can do it. So remember, in lithography, they can do things because of the way how they use the light. They can really pattern straight lines in one direction, and they much prefer to do that in one direction than in two directions. To perform a cut requires them to have reasonable sharpness of that image in the other direction. And I've shown pictures of SRAM with litho etch, and without litho etch, where those ends were badly rounded, and that's the same thing that we would have had. I'm sure they could do that with pins as well, but some of these pins would have been rounded. There would be a variation in the thickness, and it would have been bad. Plus, the way how they do it is not just litho etch. It is that self-aligned double patterning. So they print one thing and you get two pins for free, and then they cut. Okay. A little more about the design kit here. All of you have seen the design kit so far, so I don't have to spend too much time on that. I mean, you've seen it in 151, you've seen it in 251A. We're going to dive a little bit more into things that you'll find in the design kit. In there, a little deeper dive into these Liberty files. But for now, what we know about the design kits is that you will find physical views like the layout and schematic with appropriate abstractions, like there will be a left for a cell. There will be a netlist that is you can simulate in SPICE. There will be a logical view, a Verilog model for the cell, and there will be some kind of a test view perhaps for it. And then you'll find timing, power, and also noise views for that particular cell, and there'll be a documentation. So if you look at the technology that we're using in the class now, it is a 7-nanometer predictive technology kit, or partially predictive. The transistor models are predictive. The technology is a reverse engineer of various IEDM and VLSI papers that have been published. So we essentially took this technology and made it look like what has been published for 7-nanometer technologies. And what you'll find in there is multi-threshold standard cell library, 45 IO pads, something that really enables us to do things with some kind of SRAMs, no SRAM compiler. There's a design rule manual and a decent amount of documentation that enables us to do things. So, really good approximation of what we will find in practice out there. Now, before diving into what we find in the standard cell, inside of a standard cell, we would like to take a look at what practically delay is. So all the time, everything we have done so far, we have assumed that the inputs really rapidly jump from 0 to VDD or from VDD to 0. And the propagation delay is 0.7 times R equivalent times CL. And we took R equivalent as we did last time around and found it as an average between the two values of the ratio of the current and the voltage and multiplied it with an equivalent load capacity. Now, in practice, we never have a transition at the input of a gate like that. Our transition at the input of the gate has some kind of a slope. How does that affect the propagation delay? Well, the NMOS transistor will not turn on instantaneously. It will turn on gradually. We're actually going to see the impact. Remember, I would have drawn this now, but I'm afraid of doing so. We would have seen, for a very sharp transition, we'll be jumping up from the low VDS versus IDS versus VGS curves to high IDS versus VGS curves, as I've drawn in the last lecture, and you have seen those circles over there. Or and we would have, for a sharper transition, we would have had more of an equivalent current, less of a resistance. For a slower transition, we would have had less of an equivalent current and higher equivalent resistance. So what is that equivalent resistance that corresponds to finite slope? That's what we're going to do in the next 10 minutes. And I was going to derive that, to try to derive it. But I'm afraid to do that. So, stay tuned. And I do have the notes that I'll go through. Propagation delay. A few things that are good to remember. Our propagation delay is equal to ln of 2 times RC, which is 0.7 R equivalent times CL. If I care about the rise time, you'll find two different rise times often in standard cell like this, defined as time that it takes from 10 to 90 or from 20 to 80. To go from 10% of the waveform to 90% of the waveform, or from 20% all the waveform to 80% of the waveform. The textbook that we have, that we've been using, has been defining rise times from 10 to 90. However, many of the standard cells in practice actually go from 10 to 80. There's a big difference in that. Those two times are very different. 10 to 90 is approximately, if you go and find out what is that log, that is about 2.2 R equivalent times CL, or roughly 3 propagation delays. So a cell that has a propagation delay that is X will have a transition in the output that is 3X from 10 to 90. Or if we define it from 20 to 80, which is what we'll find in the standard cell library, it will be twice the propagation delay. Just something that is good to remember. These logs are a useful thing to remember, such that you can eyeball things. So in order to find what is the actual slope dependence, we can try to go and do some integration. And that would not be pretty, probably. I would not put myself to that, but I was going to write that over there. I would try to find out what is the equivalent I out times CL times PV out over DP, and I would try to subtract NMOS and PMOS currents. One thing that I would try to say here is that in scale technologies, the ratio of VDD to threshold is relatively low. So it is very safe during these transitions to assume that when NMOS turns on, PMOS is pretty much off. Right? So it is all what we need to consider is just a single transistor. And we would like to use the simplest model that will work for us, which is a linear model of the dependence of ID versus VDS. So for most of the reasonable inputs, we can ignore the PMOS current if we are just looking at the falling edge at the output or high to low transition. And then we would like to find out essentially what's the response of the current ramp that starts when input is equal to the threshold voltage, that model threshold voltage that is slightly higher than our regular threshold voltage. So I can write this down as an integral. I can essentially break a set of equations. Those equations would be the dependence of V in relationship to that dependence of IB on V in, and then finally V out on IB. The first two are linear, the last one is a log, and I'm sure you can solve that. Yep. Give yourself 45 minutes and it's totally doable. Now, instead of that, we can do a graphical analysis. That is what we're going to do. We're going to take a look at V in with a slope that is corresponds to some kind of a P rise, and we'll define that P rise from 10 to 90 or 20 to 80. And we are going to compare it to a step input where P rise is instantaneously rises from 0 to 1. We're going to take a look at what happens to I out. I out does not change until the NMOS transistor comes on. Right, I mean, as long as it is below the threshold, the I out, or which is essentially the IDS of the NMOS transistor, is going to stay low, it is going to stay 0. And then, when it reaches the threshold, the current will linearly increase according to our model. Remember, I'm using a linear model of the dependence of IB to VGS, and VGS is equal to V. You can plug in any other model that you want, but it's just going to make life more complicated, not necessarily more accurate. And then my V out is essentially the charge that is accumulated on the output capacitance, which integrates I out. So first, whenever I integrate something that is linear, I'll get quadratic dependence. Then, when the current saturates, they'll turn linear dependence. So I can go ahead and derive that, but instead, I'll do it this way. I'll take a look at my rising waveform with a finite slope and compare it to the instantaneous jump in input voltage. I do expect that my finite input slope is going to cause longer delay. I'd like to find out how much longer is the delay compared to the ideal step. Okay, so I'm trying to mentally prepare myself to the output that is going to say that my propagation delay is equal to the T step plus a component that corresponds to the rise time. So let's model that. So I got both finite slope an instantaneous t-step over here. And to make this really convenient, I was taught, this trick by my colleague Elad Alon. We have the first derivation over here. Elad came up with a very elegant one. And he might have gotten it from someone else, but we'll give credit to Elad for now. Instead of aligning the beginning of the transition, which is when both of these waveforms cross VDD over 2, we'll go ahead and align the ends of the transition. When the output crosses VDD over 2, that's the end when we time that. And then we are going to try to find out how much earlier does this transition have to start in order to match the same propagation. So we want the output to cross for t-step and t finite slope at the same time for VDD over 2. We would like to know how much earlier does the transition that has a finite slope need to start in order to match. It is a very elegant observation over here that V output is set by charge removed from the capacitance, since we are essentially discharging that capacitance. In both cases, we need to remove exactly the same amount of charge, no matter how you cook it, the same amount needs to be removed. So in one case, we need to remove the box over here. In the other case, we are removing the triangle. How do we make the area of this box equal box, so that rectangle equal to the area of a triangle? Well, we do that by making QR equal to QS. When does that happen? Well, at this point, when the step crosses ID set over 2. That basically means that my transition needs to produce that such that the input crosses that value at some point that corresponds to the time. So doing this calculation with a linear model is relatively straightforward. So I'll find out that in order to make this equal to that, I need to find a point where my D in crosses the point D hot, which is VDD plus the threshold divided by 2. That's a half of my transition going from 0 current to the max current, 0 current corresponding to VTHC, max current corresponding to VDD. So I need to, I can do all kinds of things over here, but essentially I need to find out when does this waveform cross. So that's the two of them on a line. I'll plug in a model that ID sat is proportional, linearly proportional to VDD minus VTH. I'll find that it's E half. I'll find the additional time that is essentially proportional to the slope. That is that time that we need to add to the step response to get the actual propagation delay that corresponds to the slope input. So delta T slope is going to, from very simple evaluation over here, going to be equal to VTHC divided by 2, divided by some kind of a constant that corresponds to the rise time, and that is the slope of the equal curve. I can plug in either one of these that I want over here. Lower standard cells nowadays use T rise 20 to 80, so that is essentially 2 times of the propagation delay at input. Remember that input rise time is twice the propagation delay of the previous cell, the cell that drives this one. So I got my answer. My propagation delay over amp is equal to the propagation delay over step plus something that is proportional to the slope. And that proportionality is VTHC over VDP times PP here. predefine the PP int, the rise time is 20 to 80 value. So to summarize all of this, my PP RAM is equal to PP step plus a component that is proportional to the input slope. Input slope in turn is proportional to the propagation delay of the previous cell. I don't have to keep that in mind. I can just keep the two values to keep track of the two values. So if I would like to find an average, well, this would be an average of the two thresholds, P and N. And you know, the threshold is somewhere between 1/3 and 1/2 of a BTP now, so you can find out what is the effect over there. It is, you know, about E. This is not an insignificant effect. It is a quarter of the P rise, and P rise is twice the propagation delay of the previous one. So it significantly impacts the overall delay. So when we are trying to time a circuit, as we are going to cover in the next lecture, when we are doing static timing analysis, we need to keep that track of two things: P step and P rise, or the actual delay and the rise or a fall time. You'll find out in CAD terminology or EDA terminology, these things are going to be associated with different kinds of things. One thing will be called drive strength. Drive strength is essentially R equivalent. The lower R equivalent, the higher the drive strength of a gate. You've probably seen in standard cell libraries, we have different sizes of gates for each function. We have X1 inverter, X2 inverter, and so on. That simply means that X2 has twice the drive strength or half of the resistance. Then the other thing that we'll need to know is we'll need to characterize the load. And the load is the sum of all the capacitances that are being driven by a particular gate. We should be able to look those up, plus add any wiring capacitance that we have. And finally, we need to account for input rise and fall times. Oh, there is one more catch here. And I'll go over this relatively quickly. Remember in 151 to 51A, we talked about the dependence of the propagation delay on the order of switching, input switching. So remember I said, if my top input to the stack arrives first, and the bottom of the stack arrives last, that's going to be slower than the case when the bottom arrives first and the top of the stack switches last. Why? Yes.
Question of because in one scenario the intermediate node gets starting first.
Yeah, exactly. In this case, the intermediate node will be the capacitor that we attached to it. It will be discharged first, and we have less work to do in order to bring the output down to ground. Now, what happens if both inputs arrive at about the same time? Is that better or worse in either of those two cases? And I'll give you 30 seconds to think about that. what happens when both of them switch simultaneously? Is that fair? It is actually worse. Why? In addition to a capacitance to ground from this middle node, there is another capacitance from the input to that middle node. So what happens when this input jumps up? And I get a series connection of capacitances. This input node is actually going to jump to some value that is proportional to the ratio of those two capacitances, EECS and this factor. So we actually have to do more work than either of the previous cases to discharge low electric capacitance. It really depends. Oops. How close these things are and what kind of a gate are we dealing with. That's usually an increase of timing by like 5%. But in some cases, it's been reported to be like 25%. 25% is unlikely. So I just had some really good news about 5 minutes ago that I said I don't have to run spice analysis in order to find the timing of a digital circuit. I just need to annotate propagation delays and rise times, and I should be able to statically find any gate, and that's going to be infinitely faster than trying to spice this whole microprocessor. And then I just threw this monkey wrench into it, saying that if the two signals arrive close to each other, that the whole thing is invalid, and there could be some kind of a triangle with this. What do we do about this? What would you do about this? I mean, this is awfully complicated and it's really inconvenient. So you're a CAD designer, CAD developer of late 80s, early 90s. What do you do? Come on, I mean, you got it. I mean, you're almost would be PhD students. What does an engineer do in a situation, in a difficult situation like this? You ignore it and proceed like no way. It's like, why? Why you can ignore it? It's a rare occurrence. Signals rarely arrive at the same time, and there'll be some impact on time. And then what do you do after that as an engineer and a business person? You come up with a heuristic to accommodate for that, and you sell a new license that before accident does the full sign-off time. What does that, what does the sign-off time do? One of the components of sign-off time. It figures out if the two signals are arriving close to each other within some picoseconds. And then what does it do? Apply some penalty to the timing of some, increases the timing of a gate by some fraction of 2%, 5%, 10%. We don't actually know. But that's the difference between, say, running design time, which is a synthesis type of a timer, and prime time, which is a sign. Okay. Start thinking like engineers. Right. First, assess how big of a problem it is. If you can live without it, then just move on. We apply some margin to the final result. But then, when people start complaining, we add a new license. We fix the problem and add a new license. That fixes that. Yes.
Could you please go over again how it increases when both A and B are present?
Okay, I will cover that again. The reason why the delay increases is because there is a capacitance. I would have loved to draw it. I can draw it maybe over here, if this works. I need to go. This is hopeless, I think. Oh, he has one. Let's make it permanent over here so nobody can. Thank you. Let's make sure this one is okay. Yeah, try this. So, and there is something over here, and I have two inputs switching. Essentially, what happens here, I have two capacitors. As this guy switches, what happens to that node? It started from, in the worst case, from some value VDD, and then it will jump up to a new value that is equal to what? The timing is just right. This signal just went up, some picoseconds before that one. It's, capacitive sharing is instantaneous, essentially. So this will go to VDD plus what? C stack versus CGS. Come on, you guys know this. Capacitive divider. Plus C GS. I mean, this can be big in practice. This guy will start conducting and it will discharge. But essentially, I see a bump here and then it goes down. Take a look at, when you spice your gate, you can see a waveform that essentially does that. You see that bump and then the discharge. That adds a little bit to the delay. Sign of timing this is not the only thing that sign of timing does. They do more accurate analysis. It would be one of the examples. Okay. Why we don't do that during synthesis? Generally, we don't do it during synthesis. Because synthesis goes through too many options. Tries a lot of stuff, and doesn't want to be slowed down unnecessarily. Perhaps some of the modern synthesis tools may be doing more. Okay, standard cell library. So what you'll find inside of a standard cell library, uh-oh, my stuff is going over here. Instead of a standard cell library related to this, we need to get some of the views. So we get the functional information, which is a variable model, time information, which is a function of the input slew or input time and hold times, intrinsic delay, which is a step delay essentially, output capacitance as well as input capacitance, and that usually is all nonlinear. Then you'll find out physical power characteristics, noise, and stuff like that. And then a chunk of the standard cell library will have wire load models. What are wire load models? They are so-called statistical wire load models. They have been collected from a range of designs that essentially says, oh, okay, my block is of this size, and my gate drives this much of a fan-out. This is the likely amount of wire capacity. Statistically, will add some wiring fan-out to each design. When you look through the standard cell library, when you go fishing through the standard cell library, in old times when synthesis was just a dissertation of, it was developed, I believe IBM first, but dissertations in Berkeley that essentially resulted in formation of synopsis. They use linear delay models. Same linear delay models that I've just shown, where they could say that they use kind of strange names, non-circuit design. This is kind of makes sense to a CAD person, doesn't make sense to a circuit person, but they are looking at intrinsic delay, which is our step input delay that corresponds to the step input. There is a transition time. There is something that they call the connect delay, and there is the edge rate delay. If you add together the edge rate delay and the intrinsic delay, you get the actual delay of the cell. They're keeping track of each of those separately, and then you can tally that. And I think Synopsys, if you feed a library like this, the Synopsys will still do it and report timing exactly the same way as we have done here. But that is not very accurate because many of these things are not. So people have moved away from this linear characterization of linear drive strengths, linear capacitances, and linear impact of drive strength. The way how it is characterized now is all the delays, essentially dependence of a delay on capacitance and input slow time are nonlinear. So in order to find out what is the actual propagation delay, what we need to do is, instead of trying to solve some nonlinear equations, we do it as a table lookup. It is a two-dimensional table lookup that I would try to draw here. It's a two-dimensional table lookup for both variables that we need to look up. Remember what we need to carry for each gate. Propagation delay and slew rate, or rise or fall time. Each of those is a function of what? Output capacitance and input transition time. Slew rate, rise or fall. So we are going to index this two-dimensional table by rise or fall times and the capacitance in order to get the output propagation delay, and the same thing for the output transition time. We said that they're roughly with around 2x of each other. Yes.
What happens if the given combination of variable is not available in the annuity?
Brilliant question. What happens if the input combination, and most likely input combination, is not going to happen in a table? So I'll ask engineers in this, if there are any engineers in here, what are you going to do if you don't find the exact value of the input indices which are here? So this is cell rise and rise transition. So what would be what would you do?
Approximate.
Yeah, interpolate between the two. And depending on how much it used to be a linear interpolation early on. Now it is more like some kind of a smooth and higher order interpolation. And if you look at these, the delay template here is, so it can be a 7x7 type of a matrix, so for 7 inputs or 7 capacitances, 7 rise times, it's tabulated. The ratios here are, not quite 2x as I told you, but they're reasonably close to each other. So yeah, if it is not quite in there, nonlinear delay model is going to go and interpolate the points into dimensions and find what is the closest thing out there. Now, the actual modeling nowadays is not done based on resistances and capacitances. You are still characterizing it based on the input transition times and the output capacitance, but the engine that does the calculation is based on composite current source. Why is it so? Because of that funky thing that I mentioned in the previous lecture or the lecture before, is as my output transitions, I have this kink in the middle of the transition. Does anybody remember why do we have that kink? Why does my output, this is the real output transition. Why do we have the kink in the middle? Why does my transition slow down? Decide to slow down right on the VDD over 2 point. Talk about it last time. I'm gonna stop. Sorry for why. I think you know. Yeah, gate capacitance increases plus is multiplied. So it is, it starts nicely and then sees right in the middle higher capacitance and slows down. So it's nonlinear and it's nonlinear multiplied. And where do we want to time this? Where do we want the timing to be accurate? Right around there. That's where our 50% of our transition, and that's where we lose our nice, sharp transition. So there's quite a bit of uncertainty. The way how they fix that, and I'm not going to dive into this, is they model gates not as resistances anymore. They model them as currents. The lookup is something that is interpolated between the two currents that are bounding this and the load capacitance. And the current is being looked up based on the slope of the load. Now, this is, gets messy because we are going to add a nonlinear capacitance that Liz reminded us that exists with some linear capacitances that depend on the wire load model that are going to smoothen this whole. So depending on what we are driving, we're going to use a different composition of these current sources. Too much, but that is what is happening inside of a time nowadays. So if I'm not thinking, I'm very fast. So I managed to get through 46 slides in an hour and 20 minutes. But essentially, we have been talking about standard cells. We have been talking about composition of a standard cell library and how we calculate the weights. That's all I think we could cover for today. We're going to try to send you feedback on your proposals, project proposals today. We'll divide it up between the instructors. And then you need to produce your reports in 2.5 weeks, midterm report. Remember, these are literature reviews. In the next lecture, I am going to cover timing. So we'll go over static timing, where, how do these gate delays actually end up being added up together. We'll revisit the flip-flop-based timing, and then we'll cover latch-based timing, which we haven't seen. Okay. And then we'll talk about latches and flip-flops. Any questions here? And I will go read again a whole bunch of other things and practice, to figure out what happens. Why do I have problems with inking? And why does the old computer not have that problem, and why the new ones do have, which is the biggest mystery of them all. But the old computer is too old and doesn't have enough, horsepower to run this kind of stuff. And then I'm going to decide if you're going to continue having zooms. This thing does not want to continue